In this example, a hollow cylinder beam ABC is loaded with a uniformly distributed load along ABC with 3 kN per meter. The beam is built in at point A, or in other words, fixed supported at point A and roller supported at points B, while from the figure it shows clearly point C is free. The beam is made of structural steel with E 200 GPa. The outer diameter of this beam is 100 mm, while its inner diameter is 60 mm. By using the finite element methods, solve the problem and obtain the nodal displacements, or in other words, to obtain the unknown degree of freedoms. B, to calculate the force and moment reactions at A, and the last one to calculate the shear force at midspan of member BC. The first step that we have to do in this case is to sketch the model and to create the nodes, elements, and determine the degree of freedoms. So the first step is to create the nodes. As in this problem, we have 3 points A, B, C, so we can create 3 nodes A, B, and C. Then, by using this node, we can create the elements. So we can create 2 elements in this problem. Element 1 is connected by nodes A and B, while for element 2 is connected by element B and C. The next step is to determine the degree of freedom at each node. So, in this case, as it has been built in, so the deformation behavior at point A, it will go straight first before it goes down, and then he go up again at point B and goes down. At point B, it will have something like this, very sharp like that. So meaning that at point A, we're not going to have vertical deflection as well as the rotation. We're not going to have any rotation at point A because it's a built-in. But at point B, vertical deflection is 0, but we still can have the slope at point B. At point B, we can have a slope here, theta. Okay, either positive or negative, we're going to see that. And of course, at point C, we can have the deflection as well as the theta here at point C. So we can define at point A, VA equal to 0, theta A equal to 0. At point B, VB equal to 0, but theta B is unknown. Even though VB is 0, but we still have the rotations. While at point C is a free point, then you're going to have both VC and theta C. So in this case, we have 3 degree of freedom, theta B, VC, and theta C. The next step is to obtain the stiffness metric for each element by using the K metric for beam element. So, in this case, as the beam is made from the same material and having the same cross section from A to C, then we can say that the I, or the second moment area for element 1 and element 2 is equal or similar. By using the equation for circular or cylinder, the I is equal to 4.27 times 10 power negative 6 meter power 4. So by knowing the E is 200 gigapascal, I is already calculated, and L for each element we can calculate the stiffness metric for each element. For element 1, the L is 4 meter. Then we can calculate the K matrix for element 1. Please take note, for element 1, as we know that the VA, theta A and VB equal to 0, so we can eliminate this column from the beginning. So that we just focus on the column that is unknown the degree of freedom. So by replacing those values with E 200 gigapascal, I 4.27, L is 4 meter. Please do not forget this 3, power 3 here. And all those values is coming from this matrix. For example, the first value 24 is equaling to this equation 6 times L. As our L is 4, therefore the first value is 24. 6 times 4, 24. The second value 2 times L square. So our L is 4, so L square is 16. 16 times 2 equal to 32. That's how we obtain 32. And the rest value as follow to this equation. Then by expanding this equation, then we obtain our K1 matrix. And then we have to do the same thing for K2 or for the second element. In the second element, please take note that our L is now 2. Okay, according to this element 2, from B to C is L is equal to 2 meter. So by using the same I, the same E, and the L is equal to 2 meter, so that we can calculate the K2 by knowing the VB is equal to 0, so that we can eliminate the VB column from the beginning. So we just fill up this matrix by using this equation. By expanding this K2, then we obtain the K matrix for second element. Please do not forget to write this notation. It will help us later when we are going to assemble into the global matrix. The third step is to obtain the global stiffness matrix for the whole structure. For that, we have to recall our K1 and K2. Then we have to insert this K1 and K2 into our global K matrix. So as we know, the VA, theta A, VB is equal to 0, so that we can eliminate this column straight away, and then we just need to insert those active value from the K1 according to its position. For example, theta B, VA, so theta B, VA is 320.4. And similarly, we do the same for the rest value according to this equation. Very similar to bar and the truss element problem. Next, once we insert the K1, the second step is to insert the K2 matrix into this global matrix. So for element 2, the K matrix is started from theta B and VB. So theta B and VB, so we just need to include. We need to get the summation later on. So once we insert the K2 into this global matrix, the next step is just to obtain or to get the summation of those values. Next step, once we have our K global, the next step to solve this problem is to apply the boundary conditions. As we know that in this problem, the VA, theta A and VB is equal to 0. So in order to reduce this matrix, or in order to obtain our displacement, we have to eliminate those row that having zero value. So for example, VA equal to 0, so we eliminate row VA, and then we eliminate row theta A, and the last one we eliminate the row for VB. So finally we have the reduced K matrix, the reduced K global matrix given by 3 times 3 matrix, only for those unknown, dedicated for those unknown degree of freedoms. As we know, in this problem, the beam has been loaded with the uniform distributed loads. Therefore, we have to convert this uniform distributed loads into equivalent forces and moment by using the equations that we have defined in the previous video. Please take note that the uniform distributed loads has been applied for both element 1 and element 2. So for that reason, we have to calculate the equivalent forces and moment for each element first. For element 1, as we know that the P is equal to -3 and L is equal to 4, so by using this equation, we can obtain this value. For example, the 6 is by using this equation. P is -3 times 4 is 12 divided by 2, so equal to -6. For the second term here, by using this equation, PL square over 12. P is -3 times L square. L is equal to 4 for element 1, and divided by 12 is equal to -4. And this one is for the third terms, and we're using the last one for the fourth term. So the first term is dedicated for vertical force at A, FAY. The second term is moment at point A. The third term is for vertical force at point B, and the last term is the moment at point B. We do the same for the second element by using the same equations, but for the second element, the L is equal to 2. P still equal to -3. For example, the first term here, P -3 times 2 equal to -6 divided by 2 equal to -3. The second term, by using the same equations, we can obtain for the third equation as well as the fourth equation. For element 2, the first term is dedicated to FBY, or the vertical force at point B, and moment at point B for the second term, while for the third and fourth terms is dedicated for FCYM and MC, the vertical force at point C and moment at point C. So by having these two equivalent forces and moment for element 1 and element 2, the next step is to assemble these two equivalent forces and moment to obtain the global forces and moment. So we just need to assemble it. So we know that in element 1 we have FBY and MB. In element 2 we also have FBY and MB. So for FBY and MB, we just need to get the summations, so that the final equivalent forces and moment will be this one. Or we can put here the physical interpretations of those values that we have obtained at each node. Remember that at node A, it has been fixed joints. So meaning that it's going to have reaction. That's why for at point A, you need to add with reaction FAY. And for the moment, we need to add the reaction moment at point A. Similarly, for point B, as it cannot move in Y direction, then it's going to have reaction moment in y direction. The force in y direction. That's why for FBY, you need to add with reaction FBY. For the rest value, there is no reactions. Only at these 3 points that has reactions. The next step is to set up the system linear equation by using the same equation, which is F equal to KU. So in this case, we have 3 unknowns, which is theta B, VC, and theta C. So when we talk about theta B, it's about rotation. So rotation is caused by moment. Okay, is caused by the moment. So for theta B, then we need to use its load coming from moment at point B. So for VC is the vertical deflection or vertical displacement. For displacement is always caused by the forces or the force. For VC, then we need to check for point C and must take for the force. So for VC, we must use FCY that cause the displacement. And for theta C is about rotation. Again, for rotation, we need to refer to the moments because rotation is caused by the moment. So for theta C, then we need to use moment C. That's why we have this value coming from MB, FCY, and MC. So by knowing these 3 values, then we can use the calculator to obtain the unknowns, as shown in this slide. For question B, the question asks us to calculate the reaction, force, and moment at point A. So in order to calculate the reaction, moment or force, we have to go back to our K global. So from K global, we have to use the equation for VA and theta A. For example, in order to calculate the reaction at point A, so we have to refer to VA and theta A. VA dedicated for force, theta A, which is rotation, is dedicated for moment. So for reactions, okay, for example at point A, so we look at point A, so we have this equation, negative 6 kilonewton coming from the distributed loads plus with the reaction. So do not forget this value. So FAY is equal to this one, which is equal to this line. So this line we have 320.4 times theta B. That's why we have this equation. For moment at point A, then we have to refer to this second line using the theta A equations and refer to back to our loads. For this one, at point A, we have MA is equal to negative 4 kilonewton plus reaction moment A. So that's why we have here. This negative 4 kilonewton is coming from the distributed loads. So by using this equation, then we can solve for reaction moment. If question asks to calculate the reaction at point B, so at point B, we only has reaction force, as we cannot have deflection in y directions, but it still can rotate. That's why we only has reactions in force. So to calculate the reaction force at point B, so you must take all this value. Okay, the negative 9 kilonewton is coming from the distributed loads, is the applied loads to the system. So that's why we have to include this one, okay, so that you can solve the reaction at point B. The last parameters that we're going to discuss, or the one that we're going to calculate after this, are bending moment and shear force. The bending moment is derived from the deflection equations, differentiate by 2 times, then we obtain this equation given by this equation, and the shear force when we differentiate the deflection equation by 3 times and we obtain this equation for the shear force. So please recall that in one element we have Vi and theta I, Vj and theta j. So in order to calculate the bending moment and the shear force, we need to know this displacement value or the deflection value at each node. And then the other parameter that we have to know before we can calculate the bending moment is the value of natural coordinates. If we notice in this equation, we have this equation zeta here. We have zeta here, and here. So this zeta is actually the natural coordinates, and the natural coordinate is always in one element starting with -1, and it will end with 1 when x equal to L. In between, from x equal to 0 until x equal to L, the zeta can be defined by using this equation. So the LE is the length of the element, which is known. Xi is the value of x at the beginning. So in one element, x always start with from 0. Okay, so if the question asks us to calculate the bending moment at the midspan, meaning that at the midspan somewhere in the middle. So we know that at the middle, x or L, x is equal to L over 2. So by replacing L over 2 to this equation, then we will obtain zeta is equal to 0. And also, if the question asks us to calculate the bending moment or the shear force when x equal to, for example, 1, so you just need to replace 1 into this equation so that we can obtain what will be the value for zeta. So remember, at the beginning of element zeta equal to -1, at the end of element zeta equal to 1, and whenever question asks to calculate the bending moment or the shear force at the midspan, meaning that at the middle of the elements, so zeta is equal to 0. Back to the question, to calculate the shear force and bending moment at the midspan of BC. So BC is element 2, so meaning that our I and J will be point B and point C. Node I will be node B, node J will be node C. So later you have to replace this VI and theta I with VB and theta B. While for VJ and theta J, we need to replace with VC and theta C. So all those value, all those degree of freedoms value are known from the previous solutions. We have defined VB equal to 0, theta B, VC and theta C as shown in this figure. And as the question asks to calculate the moment and the shear force at the middle of BC, so we know that at the middle of the element, the natural coordinate is equal to 0. So by knowing all these parameters, so we can expand the moment equations. So here we just replace the VI with VB, theta I with theta B, while VJ and theta J we replace with VC and theta C. And we know that our zeta is equal to 0. So by replacing 0 and those value for E and I and L, then we can obtain our moment is nearly to negative 2000 Newton meter. And we can do the same for the shear force. Similarly, is the shear force at the midspan of BC. So we know at the midspan theta equal to 0. All those value is known. So we just need to replace into the shear force equations. So I and J in this case will be node B and node C. That's why we replace all these VI theta I with VB and theta B. Vj theta j with Vc and theta c. So in this case, it's very straightforward. It's not involved with natural coordinates. So we just need, it just depends on the degree of freedom at the nodes that we have calculated before. So by replacing all those values, then we can obtain our shear force at the midspan of BC is equal to nearly 3000 Newton. So when this equation did not involve the natural coordinates, meaning that the shear force along BC, along BC is constant. The value will be always 3000 along the member BC.